Good morning. In the last lecture, we defined a finite field and the order of a finite field. We showed that the integers modulo n is a field if and only if n is a prime number. We defined the notion of the characteristic of a finite field and proved that every finite field has as a subfield the integers modulo p, where p is the characteristic of the finite field. This proved that every finite field must have order that's a power of its characteristic. In this lecture, we'll prove the converse result, that for every prime power p to the n, there exists a finite field of order p to the n. We'll do this by mimicking our construction of the integers modulo p from the infinite ring of integers to infinite polynomial rings. This will prove that finite fields of order q exist if and only if q is a prime power.
Let me make some remarks about notation. We use little c to denote code words and capital C to denote a code. But sometimes the instructor's handwriting might not be clear, and so it might sometimes be a bit difficult to distinguish a small c from a capital C. If this ever causes confusion when you read our slides, please do ask me a question about that. We use little f for polynomials and capital F for fields. These two f's look quite different when they're written down, so no confusion should arise when you read the slides. But verbally saying things like f belongs to f of x sounds a little awkward. So, I hope it's clear from context which of the f's is a polynomial and which represents a field. We use Q for two things in this course. Q stands for the size of the alphabet, and Q will also be used for the order of a finite field. However, no confusion should arise from these two uses of Q, because in the remainder of the course, the alphabet will be the elements of the field G, F, Q. And so, Q will be used consistently to represent both the alphabet size and the order of the field on Q elements. Lastly, we use E to denote the error-correcting capability of a code, and we'll also soon begin using E to denote the error vector, which is the error that's introduced to a code word during transmission. Sometimes a sentence will use the same E twice to mean two different things. But I hope it'll be clear from context which E means the error-correcting capability, and which E stands for the error vector.
I'll prove the existence of finite fields of prime power orders by describing a way to construct these finite fields. By construction, I mean we'll describe the elements of the field and also how one can efficiently compute the addition and multiplication operations in that field. I'll show you the construction mostly by analogy to the construction we used to derive the integers modulo p, or finite fields of prime order, from the infinite commutative ring of integers. So instead of using the ring of integers, we'll use the ring of all polynomials over a finite field. Let's define these rings. I'll let F denote any field. F square brackets x denotes the set of all polynomials in X with coefficients from F. I'll call this the set of polynomials over F. Addition and multiplication of polynomials in f of x is done in the usual way. But the important thing to remember is that the coefficient arithmetic is done in the field f itself. Let me illustrate this with an example. Let's consider the set of polynomials in X over the integers modulo 5. I have two such polynomials here, one of degree 4 and the other of degree 5. When I add these polynomials, I add them as I would normally add polynomials, but remembering that the coefficient arithmetic is done with integers modulo 5. So, for example, when I add 3x to the fourth and 2x to the fourth, I get 5x to the fourth. But 5 is congruent to 0 modulo 5. So, in the set of polynomials over Z5, 5x to the fourth equals 0. And that's why the 5x to the fourth term doesn't appear in the sum. Similarly, 4 plus 3 is 7, which is congruent to 2 modulo 5. I can also multiply polynomials together. For example, the product of the monomials 3x squared and 2x squared is 6x to the fourth, which I can write as x to the fourth, since 6 is congruent to 1 modulo 5. As a quick exercise, compute this product and check that you get this polynomial. This will help you get used to the fact that coefficient arithmetic in this example is done with integers modulo 5. A basic fact is that the set of all polynomials over a field F is an infinite commutative ring. It's infinite because it contains infinitely many polynomials. For example, the monomials 1, x, x squared, x cubed, and so on. It's easily seen to be a commutative ring because a set of polynomials with the operations of addition and multiplication of polynomials satisfies the 8 axioms of what it means to be a commutative ring. I'll describe next the main ideas behind our construction of finite fields from polynomial rings. The construction will be closely analogous to our construction of the field of integers modulo p from the ring of integers. Let me first recall that first construction for you. So we started with this infinite commutative ring of the set of integers. To convert this to a finite ring, I select the modulus n at least 2, and then define a relation on pairs of integers. Namely, a is congruent to b modulo n if n divides a minus b. This relation is an equivalence relation, and so it partitions the infinite set of integers into a finite set of equivalence classes, namely the n equivalence classes represented by the numbers 0, 1, 2, up to n minus 1. As we noted, this is now a finite commutative ring, the ring of integers modulo n. Finally, to get a field out of this ring, we specify that n must be prime. And then we proved that the integers modulo n is a finite field of prime order n. Our construction for new finite fields will simply replace the ring of integers by the ring of polynomials over the integers modulo p, where p is a prime. This, again, is an infinite commutative ring. We'll then fix the modulus f, which is a polynomial over Zp of degree n, which is at least 1. And we'll define an equivalence relation on the set of all polynomials. Namely, I'll say that two polynomials g and h over Zp are congruent modulo f if f divides g minus h. This equivalence relation divides the infinite set of polynomials into a finite set of equivalence classes. And I'll denote the set of equivalence classes by Zp of x modulo f. So this notation is meant to be analogous to the notation of the integers modulo n. So now we have a finite commutative ring, and by selecting f to be irreducible, namely a polynomial that doesn't factor non-trivially, we'll see that the commutative ring is in fact a finite field and of order p to the n. So in this way, we'll convert the infinite ring of polynomials over Zp to a finite field of order p to the n. Let me give you some details now of this construction of finite fields of order p to the n. I'll be informal, and so I'll do this mostly by analogy with the case of integers modulo p. But I hope that since you understand how the integers mod p were constructed, the ideas behind the construction of finite fields of order p to the n will seem quite intuitive. I'll need the notion of polynomial division, which I'll remind you of next. So let f and g be polynomials over the field f, where g is non-zero. Then, by long division, we know that there exist unique polynomials r and s, also with coefficients in f, such that f equals sg plus r, where the degree of r is less than the degree of the divisor g. Here, s is the quotient of the division and r is the remainder. I'll mention that by convention, I'll take the degree of the zero polynomial to be minus infinity. This is just a convention. Some textbooks take the degree of the zero polynomial to be 0. Others might say that the degree of the zero polynomial is undefined. I'll be consistent and always take the degree of the zero polynomial to be minus infinity. So let's work out an example of polynomial division. Let's divide this polynomial of degree 4 by this polynomial of degree 2, where I'm considering both polynomials to be over Z5. So I've written here the divisor g of x, and this is the dividend f. The first quotient term is a monomial you need to multiply 2x squared by to get 3x to the fourth. And this monomial is 4x squared, because 4 times 2 is 8, which is congruent to 3 modulo 5. So I select 4x squared as the first monomial in the quotient and multiply that with the divisor to get this polynomial. I subtract to get x squared plus x plus 1. The next monomial in the quotient is 3, because 3 times 2x squared is 6x squared, which is the same as x squared. I subtract to get the remainder 2x plus 4, which has a degree less than the degree of the divisor. And so that terminates the long division. So f is a quotient times the divisor plus the remainder. Let's now take a look at the construction of the ring of polynomials modulo little f, where f is some reduction polynomial. This construction is analogous to the construction of the ring of integers modulo n, a finite commutative ring from the infinite ring of all integers. I'll need the following definition. Let little f be some polynomial over the field capital F of degree at least 1. Let g and h be any polynomials over the field f. Then g is congruent to h modulo f, written in the usual way. If g minus h is a polynomial multiple of f. Here the multiple also has coefficients in the field capital F. Equivalently, we could write that f divides g minus h. And you can check that the relation of g being congruent to h modulo f is equivalent to the condition that g and h leave the same remainder upon division by f. Here are some facts about the relation of congruence modulo f. The relation is an equivalence relation, and so it's reflexive, symmetric, and transitive. Hence, it partitions the set of all polynomials into equivalence classes. The equivalence class containing the polynomial g is the set of all polynomials h over f, which are congruent to g modulo f. One can now define addition and multiplication of these equivalence classes in the natural way. So the sum of the equivalence classes containing g and h is defined to be the equivalence class containing g plus h. And multiplication of equivalence classes is defined similarly. Let me next define the set of all equivalence classes by f square brackets x modulo little f. This notation is meant to be analogous to the notation for the integers modulo n. We now have a theorem that the set of all equivalence classes is a commutative ring. You can verify the proof of this theorem as an exercise. Let's next select a convenient set of representatives of the equivalence classes of this polynomial ring. We'll suppose that f has degree n. Remember, f is the fixed modulus chosen for the polynomial ring. Now, for any polynomial g over capital F, long division of g by f yields an equation g equals sf plus r, where the quotient s and the remainder r have coefficients in the field f, and r has degree less than the degree of n. And so, since g minus r is a polynomial multiple of f, g is congruent to r modulo f. And so the equivalence class containing g is the same as the equivalence class containing r. And so we can represent the equivalence class containing g by the equivalence class containing r, where r is the unique remainder polynomial upon dividing g by f. Furthermore, if r1 and r2 are different polynomials over f, and both have degree less than n, then f cannot divide r1 minus r2, because r1 minus r2 is non-zero and has degree less than the degree of f. Hence, r1 is not congruent to r2 modulo f, and so they represent different equivalence classes. So to recap, every equivalence class of polynomials can be represented by a remainder polynomial. And on the other hand, any two remainder polynomials that are different represent different equivalence classes. Thus, we see that the polynomials over the field f of degree less than n are a complete set of representatives of the equivalence classes in the polynomial ring. Now, if we take f to be the field of integers modulo p, where p is a prime, then we see that the ring of polynomials over Zp modulo f can be written as the set of all equivalence classes represented by r, where r is a polynomial over Zp of degree less than n. How many such remainder polynomials are there? Well, that's easy to count, because each such polynomial r can be written in the form r0 plus r1x plus rn minus 1x to the n minus 1. There are n coefficients Ri, and p choices for each coefficient. So the total number of such polynomials is p to the n. Thus, our ring of polynomials over Zp, modulo the polynomial f of degree n, has size p to the n. And so we conclude that Zp of x modulo f is a finite commutative ring of order p to the n. It remains then to determine when this ring is a field. We'll do that next. Okay, so we need to determine when the ring of polynomials over a field f, modulo the polynomial little f, is a field. We'll see that this is a field if and only if the modulus little f is irreducible over the field capital F. So this will be analogous to the situation when the integers modulo n is a field if and only if the modulus n is prime. Let me define formally the notion of irreducibility. So let little f be a polynomial over the field capital F, having degree at least 1. Then the polynomial f is irreducible over f if little f cannot be written in the form g times h, where g and h are polynomials in the same polynomial ring as little f, and both have degree at least 1. In other words, f doesn't have a non-trivial factorization. I want to rule out trivial factorizations of the form f equals 1 times f, because this really isn't a proper factorization. Now, it's very important when you're talking about irreducibility to state the field of irreducibility. So little f is irreducible over the field capital F means that f cannot be written as a product of polynomials, both of degree smaller than the degree of f, where g and h both have coefficients in the same field capital F as the polynomial little f. Let's do some examples of this. The polynomial x squared plus 1 is irreducible over the field of real numbers, since it has no real roots. I'm using here a theorem called the factor theorem, which states that a linear polynomial x minus c divides little f of x, if and only if c is a root of f. On the other hand, x squared plus 1 is reducible over the field of complex numbers. And that's because x squared plus 1 has a root in the field of complex numbers, namely the complex number I. So x squared plus 1 can be factored over the complex numbers as x plus I times x minus I. Note that these two factors have coefficients that are complex numbers, but not necessarily real numbers. So we can say that x squared plus 1 is reducible over the complex numbers, even though it's irreducible over the real numbers. Continuing the example, we see that x squared plus 1 is reducible over the field of integers modulo 2. And that's because x squared plus 1 has a root in Z2, namely the number 1. Again, the key point here is that we're considering polynomials now over Z2. Hence, x squared plus 1 factors over Z2 as x plus 1 times x plus 1. This factorization seems a little strange, because the product has a middle term 2x. But remember, 2 is congruent to 0 modulo 2, and so 2x is the same as 0. So x plus 1 times x plus 1 is indeed equal to x squared plus 1 over the integers modulo 2. Lastly, x squared plus 1 is irreducible over the field of integers modulo 3, because you can check that x squared plus 1 has no roots in the integers modulo 3. And you can do that by trying the roots 0, 1, and 2. Since the polynomial has no roots in Z3, it has no linear factors over Z3, and so is irreducible over Z3. So you can see that irreducibility of a polynomial crucially depends on the field over which we're factoring the polynomials. We now have the following theorem. The polynomial ring is a field if and only if the modulus f is irreducible over the field capital F. This statement is analogous to what we proved earlier, that the integers modulo n is a field if and only if n is a prime. The proof is completely analogous to the proof of the theorem for the integers modulo n on slide 29. I'll leave the proof as an exercise for you.
In V2d, we'll see some examples of finite fields whose orders are prime powers. We'll also state some results that settle the existence and uniqueness of finite fields. Goodbye.